Welcome to day 9. You've got 3 on your homework tonight you're doing in the calculator. The rest you're going to do algebraically. First one's here, we wanted to find the points of intersection, set them equal, solve for theta. You got pi over 2 and 3 pi over 2. Check the poles, which you probably could just tell from the picture that you were going to have a spot at the pole. But the algebraic way to check the poles, set them each equal to 0 and see that there is actually some place where they are equal to 0. So we had 1 pi over 2, 1 3 pi over 2, and the pole. You're getting the ones from just subbing the pi over 2 or 3 pi over 2 back into either equation. 15, set them equal and solve. Sine and cos are the negation of one another when you have a 45-degree reference angle in the second or the fourth quadrant. So that's where we get 3 pi over 4 and 7 pi over 4 from. Sub back in to get the r value for each of those. And again, you might have been able to just tell from the picture that it was going to cross the pole, or you could have set them each equal to 0 and saw that there's a value when r would be 0. 18, set them equal to 0, you get cos is a half. That's a positive, so that's in the first and the fourth quadrants with a 60-degree reference angle. So we have pi over 3 and 5 pi over 3. Sub them back in to get 3 halves for the radius. If you graphed it, you might have seen that they crossed at the pole, or set them each equal to 0 and see that there's a value of theta that has a radius of 0. So we had the pole as well. So for this one, we get pi over 12 and 5 pi over 12. And then it's symmetrical for each of the others. So imagine you had a pi over 12 and a 5 pi over 12 reference angle in each of the other quadrants. So that's where you get the 7 pi over 12, 11 pi over 12, and so on. The radius was just 2 for all of them, and they were not intersecting at the pole. So for this one, to find when cos theta is equal to 1 minus radical 2, after you do your neatening up when you cross multiply, took the square root, and so on. You get those values of theta to 3 decimal places. Now to find the radius, you could figure out the radius nice because we had cos theta equals 1 minus radical 2. Put that in for cos theta in the 3 equals quantity 1 minus cos theta 1. Just distribute the negative and you get 3 square root of 2 for that. If you had done it in decimal form, it would have been 4.243. So we want the common interior. So I'm going to exaggerate a bit what our common interior looks like. So these are the purple sections here, and then that's the black section. So again, I exaggerated the curves on there a little bit just to make it a little bit easier to see. So we had 3 separate sections we had to look at. So our purple one was the 4 sine 2 theta. We needed that from 0 to our first intersection. Then from the first intersection to the second intersection, it would be the black function, the 2. And then from the second intersection all the way to pi over 2, when it comes back to the pole, we would need back to the 4 sine 2 theta 1. So we actually had from question 21, we had already set these two equal and found that they crossed at 5 pi over 12 and pi over 12. So we're going 0 to pi over 12 for the 4 sine 2 theta, then pi over 12 to 5 pi over 12 for the 2, then 5 pi over 12 to pi over 2 again for the 4 sine 2 theta. So you had to square them out. Then do your power reduction. And I kind of did that off to the right here. I had sine squared 2 theta, and then I did the power reduction, and then just filled them back in, so I didn't have to write the integral as many times. Do the antiderivative, sub everything in, and then I saved my times 4 until the end. So you could have had the 4 and then in parentheses everything from the start. I just saved the 5 times 4 till the very end. For the next one, We want it inside the 2a cos theta and outside r equals a. So r equals a is the one that's centered at the origin. When you set those equal, we get pi over 3 and 5 pi over 3. So the easiest way to do this is to just work with the top half here, and I traced too much there. Work with just this part and then double it. So for that, we're going from 0 to pi over 3, that first intersection. Do it for, basically, you'll do that black amount minus that green amount, and it'll give us the part we want, the red amount. So we've got from 0 to pi over 3 for our 2a cos theta one, then minus for the a squared one. After you square it out, you'll have to do a power reduction and everything. And then I just saved my times 2 till the end here. Again, you could put it towards the front or towards the beginning of the problem, or save it till the end. All right, so this one we wanted the common interior of the two. So for this, we basically are going to take half of the circle for that one. And then this is a different function. We're just doing that little inner loop. So for the a sine theta, you do a complete loop after pi, because sine theta gets back to 0 after pi. So that's the red one. We're doing half the circle of that from 0 to pi over 2. Well, notice I set equal there to find the intersections. So we had an intersection at pi, and then it's back at, our intersection at pi over 2, and then it's back at pi. Because our other one is really going like this. There's 0, there's pi over 2, there's pi. So we want that blue part from pi over 2 to pi of the a1 plus cos theta. So square things out. Do your power reduction. Now the part that's squeezed in there is on the left is our power reduction. And we'll leave this up here for a second so that you can pause it if you need to pause it, if you didn't end up getting that answer. So the new topic for today is we're going to do arc length with polar. So the general idea with arc length is the same as arc length with all of our other ones. Imagine we take little segments between points on the polar curve, allow those number of segments to go to infinity, and then add them all up. So that's what eventually leads to the integral. So we are going to use a Pythagorean theorem idea, but we first have to think of our dy over d theta and our dx over d theta. Make sure we're thinking of x and y with r's function subbed in. And this is kind of what we did when we originally did the derivative for polar functions. So x we know is r cos theta. We'll think of that as some function of theta cos theta. And y is equal to r sine theta. So that's some function of theta times sine theta. Well, moving down to the bottom, like we saw for our derivatives, our dx over d theta, we had to do a product rule. And our dy over d theta, we did a product rule for that as well. Well, f prime of theta is the same as saying the derivative of our radius with respect to theta. And f of theta, remember, is the same as just saying r. So we could have those written either way. I'm going to carry it through with the dr over d theta and the r's in there. So if we did a Pythagorean theorem, we've got our ds squared is equal to dx over d theta squared plus dy over d theta squared. We'll replace the dx over d theta and dy over d theta with what they are equal to here and here. Next, we'll multiply those out. So if you FOIL them out, notice your middle terms are just opposite signs, so they're going to wipe out. We'll then have a cos squared and sine squared that both have a dr over d theta squared, so you could pull that out. And you have a cos squared and sine squared that both have an r squared, so you could pull that out. Well, cos squared plus sine squared in both cases is just 1. So our ds squared is just equal to r squared plus dr over d theta squared. So that leads us then to our formula. If you get the ds by itself, you're just taking the square root. And because we're letting those segments go to infinity and then adding them all up, that leads to the integral. So we're doing our integral from wherever our theta value starts to wherever the theta value ends of the square root of your radius function squared plus the derivative of your radius function with respect to theta squared as well. So we'll look at just a couple examples for this. These are usually pretty quick. Some of these end up really messy, so they'll end up as calculator ones. That's why there's the 4 on the homework that are just calculator ones. After you set up the integral for those, just punch those right in. Any of the other ones are ones that should turn out pretty nice. So they tell us here we're going from 0 to pi, so we don't have to think about that at all. We'll have square root, we'll have 4 cos theta squared plus whatever our derivative of the radius is squared d theta. Well, we're doing it with respect to theta, so 4 cos theta's derivative would be negative 4 sine theta. So this is the integral from 0 to pi. If we square these out, we'll have 16 cos squared theta plus 16 sine squared theta d theta. We can split this into square root of 16 times the square root of cos squared theta plus sine squared theta d theta. Well, cos squared theta plus sine squared theta is just 1. Square root of 16 is 4. So we just have 4d theta, really. So our antiderivative would be 4 theta, evaluated from 0 to pi. When we sub in, we'll have pi minus 0, so we get 4 pi. And that's our arc length for our polar curve. Now, if you think about why that makes sense, this was a pretty simple case. In our picture there, that's a circle with a diameter of 4. And pi times diameter is your circumference, so the length of that arc, it makes sense, would be 4 pi. All right, going over to the next one, we want to find the length of one petal. If they had wanted it for the whole curve, we would still just do one petal and we would do it times 4 out front. So if you put in 0 for theta, cos of theta is 1, so you get 3, so that's where when theta is 0. So we need some time when it's at the pole on either side of theta equals 0. So let's do 0 equals 3 cos of 2 theta. Divide the 3 over, that's 0 equals cos of 2 theta. Well, the times when cos is 0 on either side of theta equals 0 are at pi over 2 and negative pi over 2. So we'll set those equal to 2 theta. So therefore, we will be at the pole at negative pi over 4 and pi over 4. So that'll be our bounds for the integral. So we're going to have 3 cos 2 theta squared for our r squared. So the derivative of our radius, we would have negative, I'm going to write it over here first. We'll have negative 3 sine of 2 theta, but then by chain rule, we'll have times 2. So that's going to be negative 6 sine of 2 theta that we'll put in for our derivative, which would then get squared, and we'd have a d theta. So this is minus pi over 4 to pi over 4. If we square those, we'll get 9 cos squared of 2 theta plus 36 sine squared of 2 theta d theta. And there's not something that we could pull out to leave us with a cos squared plus sine squared, so this is not one that we're going to be able to do algebraically. So if you could pause the video, type this in, make sure you're in radians, see what do you get to 3 decimal places. All right, so we should have got 7.266 for that. All right, so for our last one, we want to find the length of this entire curve. Well, imagine if you subbed in 0 for theta. Sine of theta is 0, so we would get 2 for our radius when theta is 0, so that's right here. If you put pi over 2 in, sine of pi over 2 is 1, so you get 2 minus 2 is 0, so that's our pi over 2. If you put pi in, we're back at 0, so pi 2 is there. 3 pi over 2, you get negative 1, so minus a minus 2 gives you 2, so we get 4, and then we're back here at 2 pi. So just doing that little thought process, then you don't have to bother tracing it. We're going 0 to 2 pi here. We're going to have square root of 2 minus 2 sine theta squared plus our derivative of the 2 is going to be 0. And then minus 2 sine theta's derivative will be minus 2 cos theta squared and then d theta. Well, I'm going to multiply those out and combine them off to the side. If we FOIL the first one, we're going to get 4 minus 8 sine theta plus 4 sine squared theta. And then we'll have plus 4 cos squared theta. Well, this is 4 minus 8 sine theta plus 4, and you can pull out and be left with sine squared theta plus cos squared theta, which that's just 1, so we're going to have 8 minus 8 sine theta. So that's not anything that we can work with, even if you pull the 8 out and have it as square root of 8, 1 minus sine theta, nothing we can do there. So take a second and sub it in your calculator. Pause the video, I should say, and then sub it in your calculator and see what you got. And we should end up getting 16. So arc length of a polar function, you do your integral square root, you do your radius squared plus the derivative of the radius with respect to theta squared. That's it for this video. Have a great rest of your day.